Section: Introduction. In this section, we explore how increasing computational power during testing can enhance the performance and quality of our models, particularly in multilingual contexts, which has not been extensively studied. We focus on reasoning language models, RLMs, like DeepSeek's R1 and OpenAI's O1 or O3, which gain significant advantages from additional computational resources when processing long chains of thought. However, most research has concentrated on English, with recent studies combining small-scale reasoning fine-tuning with increased thinking tokens during testing. Currently, the training data for state-of-the-art RLMs primarily consists of long chains of thought in English, making these models predominantly English-focused. We question whether fine-tuning these models in English equips them with multilingual reasoning skills, given that their foundational models are often multilingual, like the Qwen models. Our investigation aims to determine how much test-time computation can enhance the multilingual reasoning capabilities of these English-centric RLMs. We pose several research questions. 1. How effective is the test-time scaling of English-centric RLMs on multilingual reasoning tasks? 2. What language mixing behaviors do these models show when responding to non-English prompts? 3. How well do they perform when required to think in non-English languages? 4. How does their cross-lingual reasoning generalize to domains beyond STEM, such as humanities and social sciences? For our experiments, we utilize S1 models as our English-centric RLMs, which are multilingual Qwen 2.5 instruct models fine-tuned on a small set of English STEM reasoning tasks and have achieved top performance on English math reasoning benchmarks. Our key contributions include demonstrating that larger models benefit from cross-lingual test-time scaling, which contrasts with previous findings from smaller models. We find that this scaling is effective for both high-resource and low-resource languages, allowing our RLMs to outperform larger models in multilingual math reasoning tasks. We observe a prevalent language mixing pattern where RLMs quote non-English phrases during their reasoning process, indicating their ability to understand and generalize across languages. Additionally, we identify a strategy to control the reasoning language of RLMs, revealing that forcing them to think in high-resource languages leads to better performance compared to low-resource languages. We also note that while reasoning fine-tuning can help in specific domains, it does not consistently improve performance in non-STEM tasks and can even hinder results in areas requiring cultural knowledge. Our findings suggest that scaling up test-time computation for English-centric RLMs can establish a strong baseline for multilingual reasoning. We recommend fine-tuning these models with data-efficient methods to preserve their multilingual capabilities and suggest reasoning in high-resource languages like English and Chinese for optimal performance. Future research should focus on enabling RLMs to generalize to tasks outside their training domains and to reason effectively in low-resource languages. In the next section, we will discuss the background and related work on reasoning language models. Section Summary. In this section, we explore how scaling up compute at test time can enhance the multilingual reasoning abilities of English-centric reasoning language models, RLMs, which have primarily been studied in English contexts. We investigate the effectiveness of test time scaling, language mixing behaviors, and performance in non-English languages, revealing that larger models benefit from this approach and that reasoning in high-resource languages yields better outcomes. Section: Test Time Scaling and S1. In this section, we introduce test time scaling, a new approach that allows us to allocate more computational resources to large language models, LLMs, during inference before finalizing an answer. One application of this is increasing the length of model generation, especially for reasoning language models, RLMs, that can handle long chain of thought, COT, processes. The S1 work illustrates a straightforward test time scaling method, fine-tuning reasoning on a small dataset with long COTs, specifically using 1,000 samples distilled from larger RLMs like DeepSeek R1, and increasing the inference budget during testing. By applying test time scaling to a model with 32 billion parameters, we achieve top-tier performance in mathematical reasoning, even competing with industry-standard RLMs like O1 Mini. However, similar to previous RLM studies, our exploration of test time scaling primarily focuses on English math benchmarks. Our work aims to understand how effective test time scaling is for English-centric RLMs, particularly S1 models, in multilingual contexts across various domains. Multilingual reasoning refers to the ability of language models to tackle complex reasoning tasks in different languages. Previous studies have shown that using chain-of-thought prompting in English can greatly enhance performance on multilingual math reasoning tasks, indicating that LLMs may depend on dominant languages like English for complex reasoning. Subsequent research has looked into various strategies, such as translating multilingual queries into English, aligning representation spaces and reasoning outputs across languages, and broadening the language coverage of reasoning training data. Our focus is on how managing the length of long COTs and the reasoning language at test time impacts multilingual reasoning. One related study tried controlling the generation lengths of a fine-tuned DeepSeek R1 to 1.5B model but found that increasing thinking tokens resulted in minimal performance improvements for math reasoning in non-English languages. We believe their negative results stem from limited model parameters, as we demonstrate that larger models can benefit from cross-lingual test time scaling. We utilize S1 models as our English-centric RLMs, specifically the S1.1 variants, which are multilingual Qwen 2.5 instruct models fine-tuned on 1,000 English-only reasoning samples generated by DeepSeek R1. We selected S1 models for two main reasons. Their English mathematical reasoning capabilities are state-of-the-art, and both the models and training data are fully open-sourced. We experiment with S1 models of various sizes: 1.5 billion, 3 billion, 7 billion, 14 billion, and 32 billion parameters. Budget forcing involves techniques to manage the inference budget for long COTs, which can be achieved in two ways: truncation, where we cut off long COTs after reaching a maximum number of thinking tokens, or extrapolation, where we add tokens like weight at the end of COTs to encourage the model to continue reasoning. In our extrapolation setup, we only add weight once, as we do not see significant performance improvements from extending COTs further. For our research questions RQ1, RQ2, and RQ3, we use the Multilingual Grade School Math (MGSM) benchmark, which includes 250 grade school math problems translated into 10 languages: Bengali, German, Spanish, French, Japanese, Russian, Swahili, Telugu, Thai, and Mandarin Chinese. We check for overlap between S1's training samples and MGSM, including the English subset, and find no train test overlap. For RQ4, we evaluate on three different cross-domain benchmarks: Global MMLU, a multilingual version of the original MMLU dataset covering various subjects; Food-Oriented Cultural Common Sense Knowledge, FORK, which includes common sense questions about food customs; and Copal ID, a dataset for evaluating causal reasoning in Indonesian. We use the LM Evaluation Harness library as our main evaluation framework, employing greedy decoding and reporting task accuracy, equivalent to pass at 1. Section Summary. In this section, we introduce test time scaling, a method that enhances LLM performance by allocating more computational resources during inference, particularly for reasoning tasks. We focus on the effectiveness of S1 models in multilingual settings, exploring how controlling the length of chain-of-thought prompts impacts reasoning across various languages, while also evaluating our models on diverse benchmarks to assess their performance. Section: Baselines. In this section, we discuss our baseline models, primarily the Qwen 2.5 instruct models, which serve as the foundation for our experiments. For the MGSM, we utilize two prompting strategies: zero-shot prompting and few-shot chain-of-thought (COT) prompting, using 8 COT examples from the MGSM training set. We experiment with few-shot COT in English and in the same language as the input prompt. Additionally, we compare our results against previous state-of-the-art models and English-focused reasoning language models, like the R1 distilled Qwen models from DeepSeek. For cross-domain benchmarks, we simply use zero-shot prompting with Qwen 2.5 instruct. In our first research question, we investigate test time scaling in a zero-shot cross-lingual context, applying English-centric reasoning models to math problems in various languages. These models were fine-tuned from multilingual pre-trained models, making them suitable for cross-lingual transfer. From our observations, we note two key points. First, our model outperforms the few-shot prompting baseline of Quen across different languages in MGSM, except for English, especially when given a high inference thinking budget. Second, we find that test time scaling is effective for models with 3 billion parameters or more, with our model at 14 billion showing the most significant accuracy improvement when the maximum inference budget increases from 500 to 8,000 thinking tokens. We emphasize that a larger model capacity is crucial for effective cross-lingual test time scaling, as smaller models show minimal benefits. Our findings challenge recent conclusions that test time scaling may not generalize well to multilingual tasks, suggesting that the limitations observed were due to the use of smaller models rather than an inherent flaw in test time scaling. We propose that significant multilingual generalization of test time scaling occurs for models with at least 3 billion parameters, contrary to the previously suggested threshold of 70 billion. In our Pareto frontier analysis, we illustrate the trade-off between performance and efficiency across different sizes of our model family on MGSM. We calculate inference costs based on model parameters and the total number of tokens generated during inference, averaging across languages. Our results show that larger models, like the 32 billion and 14 billion parameter models, achieve accuracy levels unattainable by smaller models, regardless of the computational resources allocated. Even at their peak performance, the 3 billion and 7 billion models cannot match the accuracy of larger models with moderate resources. While we observe that larger models and higher test time compute lead to better performance, the 14 billion model strikes a balance by achieving over 80% accuracy with lower inference costs than the 32 billion model, making it a practical choice. When comparing against Quen baselines, we find that cross-lingual test time scaling significantly boosts accuracy for various baselines with Quen 2.5 models. This scaling benefits both high-resource and low-resource languages, with French seeing a 22% relative accuracy increase and Swahili, the lowest-performing language for the base model, improving by 23%. We also note similar performance trends for both truncation and extrapolation strategies, as our models already generate extensive reasoning chains, making further lengthening less beneficial. Similar improvements are observed across other sizes of our models. In our comparison with state-of-the-art models, we find that the cross-lingual test time scaling of our models serves as a strong multilingual baseline for MGSM, outperforming previous models that were fine-tuned on multilingual data. We believe this is due to the prior studies using llama as their base models, which produce shorter reasoning traces and lack advanced reasoning behaviors. Surprisingly, our 14 billion model even surpasses recent state-of-the-art reasoning models that are twice its size. We observe that the R1 Distill Quen model performs poorly on Swahili and Tamil, likely due to its extensive training data in English and Chinese leading to forgetting in lower resource languages. In contrast, our model, trained with only 1,000 English samples for 5 epochs, experiences minimal forgetting and better cross-lingual generalization. While the multilingual Gemma 3 models perform better on low-resource languages, this may be due to their inclusion during reasoning fine-tuning, whereas the performance gap on high-resource languages could be linked to shorter reasoning times. Lastly, we note that Quen 3 is the top-performing model, likely due to its long reasoning capabilities and extensive multilingual training data. Section Summary. In this section, we establish Quen 2.5 instruct models as our main baseline and explore two prompting strategies for MGSM, zero-shot and few-shot COT prompting. Our findings indicate that larger models, 3B parameters and above, benefit significantly from cross-lingual test time scaling, outperforming smaller models and prior state-of-the-art models, particularly in multilingual reasoning tasks. Section: Language Mixing Behaviors. In this section, we analyze language mixing behaviors in our S1 models during reasoning tasks that involve multiple languages. We observe that these models can mix languages when reasoning, especially as we scale up inference. Notably, previous studies have not systematically examined language mixing in cross-lingual reasoning, prompting us to explore this further to answer our research question 2, RQ2. We focus on two specific aspects. First, how the dominant language, defined as the primary language used in responses, changes after fine-tuning with English-centric reasoning, and second, the patterns of language mixing that S1 exhibits in its outputs. Our analysis includes 4 languages: Japanese, Russian, Thai, and Chinese, with detailed methodology available in the appendix. Regarding the dominant language in model outputs, we find that S1 and its base model, Quen, use different dominant languages in their responses. The Quen model tends to respond in the same language as the questions, particularly in zero-shot and native prompting scenarios. Even when provided with English samples, Quen continues to generate responses in the question's language. In contrast, S1 predominantly uses English for reasoning and final answers, indicating that fine-tuning on a small amount of English data can shift the model's behavior to be more English-focused. We observe similar trends in smaller models as well. When examining language mixing patterns, we note that S1's reasoning is mainly in English, with at least 92.5% of its sentences being entirely in English. When S1 does mix languages, it often employs a method we call quote and think. This involves quoting specific words or phrases from the input question and interpreting their meanings during reasoning. For example, S1 quoted a phrase in Japanese and provided a literal translation, demonstrating a deeper understanding of the mathematical relationships rather than just translating to English. This indicates that S1 retains its multilingual capabilities, allowing it to reason effectively about the questions. Additionally, we find that Russian shows the most intersentential language mixing, where sentences switch between English and Russian, which can confuse users expecting coherent responses. In terms of intrasentential mixing, we discover that over 70% of cases resemble the quote and think pattern, confirming it as the primary strategy for language mixing in S1's reasoning, even when not explicitly marked. Finally, we consider the concept of language forcing, where we aim to control an English-centric model to respond in a specific language. We are interested in whether this approach affects the model's performance in reasoning tasks. Section Summary. In this section, we analyze the language mixing behaviors of the S1 model in multilingual math reasoning tasks, noting that it predominantly uses English as the dominant language in its outputs, even after English-centric fine-tuning. We identify a key pattern called quote and think, where the model quotes phrases from the input and interprets them, demonstrating a deeper understanding of the mathematical relationships in different languages, while also observing undesirable intersentential mixing, particularly with Russian. Section: Methodology, Language Forcing Techniques. In this section, we experiment with various language forcing techniques to manage the reasoning language of our model, S1. First, we use the translated weight method, which builds on a strategy that extends reasoning traces. After the model completes its reasoning in English, we add a translated weight token to prompt it to switch to our selected language for further reasoning. Next, we implement the prefix technique by adding a translated phrase equivalent to, "Okay, let me try to figure this out," at the start of the reasoning process. We also apply the translated weight strategy here by appending the translated weight token. For the system prompt method, we translate the prompt, "You are a helpful assistant," into our chosen language and include an instruction that says, "You must think and answer only in language." The combined approach incorporates all the above techniques to maximize our control over the reasoning language. We test these language forcing methods on the MGSM benchmark across 28 languages. When given a question in one language, we require the model to reason in another. We evaluate our results using 2 metrics: task accuracy and language compliance. Task accuracy measures how well the model performs the task, while language compliance assesses how many tokens are generated in the intended reasoning language compared to others. To isolate the impact of reasoning language, we establish a baseline where S1 thinks in its dominant language, English, using the combined setup. In the in-language forcing scenario, we analyze whether we should enforce reasoning in the same language as the query, particularly for English-centric models, or allow them to reason in their natural language, which is English for S1. We provide an example of S1 reasoning in Japanese due to language forcing. When reasoning in high-resource languages, HRLs, we find that the scores are generally similar, with only a 1 to 2 point difference from the baseline, likely because these languages are well represented in the pre-training of our model, allowing effective transfer from English reasoning. In contrast, for low-resource languages, LRLs, the combined strategy significantly underperforms compared to the baseline. This indicates that English reasoning does not transfer well to LRLs, making S1 less capable in these languages. Strategies that mix English with the target language, especially translated weight and system, perform better than strict in-language methods like combined. This is because S1 can utilize its English reasoning skills while incorporating the target language, which is advantageous when training data is limited. For instance, in certain cases, the models using translated weight consistently outperform those using prefix or combined strategies by 4 to 5 accuracy points. We also observe a trade-off between accuracy and language compliance. While we can effectively control the reasoning language of RLMs in their long chains of thought, this often comes at the expense of task performance. For both the 32B and 14B models, the combined strategy achieves nearly 100% language compliance for both HRLs and LRLs but has the lowest accuracy compared to other strategies. For the 7B models, we find that a combination of all strategies is necessary to achieve high language compliance, indicating that controlling the reasoning language is complex and that different strategies can significantly impact how well S1 adheres to the specified reasoning language. Finally, we explore whether there is an optimal reasoning language for S1 by forcing the model to reason in all possible languages for each query language, resulting in a comprehensive analysis of query reasoning language pairs. Our performance comparison reveals that reasoning in HRLs like English, French, or German yields similar high performance, with English being the most effective and French a close second. Interestingly, we find that even though the model is highly pre-trained in Chinese, it is not the best reasoning language, even for questions in Chinese. Additionally, reasoning in neither English nor the query language guarantees the best performance. In fact, reasoning in less represented languages like Russian or Thai can sometimes yield the best results for queries in other language families. We also note that languages considered slightly less resourced, such as Thai and Bengali, achieve nearly 80% overall accuracy, while more low-resourced languages like Swahili or Telugu show significantly lower accuracy. Section Summary. In this section, we explore various language forcing techniques to control the reasoning language of our model, including strategies like translated weight, prefix, system prompt, and a combined approach, while evaluating their effectiveness on task accuracy and language compliance across high-resource and low-resource languages. Our findings indicate that while we can achieve high language compliance, it often comes at the expense of task performance, particularly in low-resource languages, suggesting a trade-off between accuracy and adherence to specified reasoning languages. Section: Inference Cost Analysis. In this section, we analyze inference costs across different reasoning languages. Our findings show a strong negative correlation between the number of tokens used and the accuracy of solving mathematical problems. We observe that reasoning in low-resource languages, LRLs, performs worse than in high-resource languages, HRLs, with accuracy falling below 80%. Additionally, LRLs require significantly more computational resources during testing, often using over 3,000 tokens in their lengthy chains of thought for languages like Bengali, Swahili, and Tamil. This difference in token efficiency leads to higher computational costs. For example, reasoning in Swahili demands about 3.5 times more computing power than in French for the same tasks, likely due to the larger tokenized lengths in LRLs. Next, we consider whether translating inputs into HRLs, such as English, is beneficial for reasoning tasks. Our results align with previous studies, showing that translating a question from Swahili to French can increase accuracy from 59.6 to 90.8, even when the model is not specifically trained in French. We also find that the model is less affected by the choice of query language in HRLs compared to LRLs, indicating greater consistency in achieving correct answers across different reasoning languages. Regarding cross-domain generalization, we explore whether the strong math performance of our models, trained only in English, applies to other non-math domains that require knowledge recall or cultural reasoning. In STEM subjects, we see that performance improves with an increase in thinking tokens. Our model significantly outperforms its base model, especially in Bengali and Swahili, where we see notable accuracy gains. This supports our earlier findings on strong cross-lingual in domain generalization. In non-STEM domains, we make two key observations. First, the benefits of reasoning fine-tuning are specific to certain domains. For example, while business and social sciences see slight improvements, the medical domain experiences nearly a 10% drop in accuracy for HRLs compared to the baseline model. Second, we find minimal cross-domain generalization from scaling thinking tokens. In medicine, increasing the maximum thinking tokens does not lead to significant accuracy improvements and can even reduce performance. For cultural common sense knowledge and reasoning, we observe similar trends, with minimal benefits from scaling thinking tokens. While reasoning fine-tuning enhances overall model performance, increasing thinking tokens can lead to worse outcomes, a phenomenon known as overthinking. In the global MMLU, which distinguishes between culture-specific and culture-agnostic questions, we find no clear pattern in which type benefits most from our training. Improvements in STEM are consistent, but performance changes in other domains are inconsistent. We also tested language forcing to see if reasoning in the same language as the question improves performance, but we found only minimal and often inconsistent gains from this approach. Section Summary. In this section, we analyze inference costs and find a strong negative correlation between token count and mathematical problem-solving accuracy, with low-resource languages requiring significantly more computational resources than high-resource languages. We also observe that translating inputs into high-resource languages can greatly enhance accuracy, while cross-domain generalization shows that STEM domains benefit from increased thinking tokens, whereas non-STEM domains, particularly medicine, do not see similar improvements. Section: Data-efficient English reasoning fine-tuning. In this section, we highlight that our model, referred to as S1, can still generate text in various languages and shows minimal catastrophic forgetting. This means it retains its ability to produce fluent text in other languages even after being fine-tuned with English data. In contrast, the R1 Distill-Quen baseline suffers significant forgetting for low-resource languages. This finding suggests that using a small amount of reasoning fine-tuning steps, like training S1 with just 1,000 English samples for 5 epochs, is beneficial for maintaining multilingual capabilities during English-focused reasoning fine-tuning. We also address the challenges of reasoning in low-resource languages, LRLs. Our results show that using LRLs for reasoning leads to poor performance. Additionally, the unfair tokenization for these languages results in higher costs for inference, making it difficult for multilingual communities to access reasoning models. We believe future efforts should aim to create fairer tokenization strategies for diverse languages. Regarding cross-lingual generalization, we observe that successful test time scaling occurs at the 3 billion parameter mark. Smaller models, those below this threshold, struggle with learning from long chains of thought and generalizing across languages. While there are ongoing efforts to develop English-centric models smaller than 3 billion parameters, we argue that future research should focus on multilingual reasoning tasks. This approach will not only enhance the development of multilingual reasoning models but also help us understand the factors that facilitate cross-lingual reasoning.